recording. So yesterday we ran out of time before we talked about the last part of our jury example on binomial distributions. So that's where we're going to start. It's on the bottom of page 14. So we're going to start there. Okay, so on the binomial distribution, just to kind of give you a recap. Okay, where is my pen at? Just a recap. The binomial distribution says that the probability x, big X, is equal to little x, just because I need something to write here, is equal to n use x, probability of success to the x power, and the probability of failure to the n minus x. That's what we learned yesterday. And that first one, that's a combination. So we have n objects, we're picking x of them. Okay, this question says, what's the probability that less than 3 people picked on this jury are African Americans? So it wants to know the probability that x is less than 3. What's our n? How many people are going to be on the jury? 12. What's our probability of success here? That we pick an African American? 0.6. That's where the 60% comes in. And just so we have it at the ready, what's our probability of failure? 0.4. Okay, so those are eventually going to be the values we use in our equation. So if I'm less than 3, what does that mean I can have for my potential values?
0, 1, 2, 3.
0, 1, 2. We can't be 3. Okay, so that means I'm going to have to add the probability that x is equal to 0 plus the probability that x is equal to 1 plus the probability that x is equal to 2. So using our formula up here, we plug in, we'll have 12 choose 0. The probability of success we said is 0.6, but we have no successes. Probability of failures is 0.4. How many failures will we have if we have no successes? 12. Plus, now we need to do the probability that we have 1 success. The 12 choose 1, 0.6 to the first power. How many failures will I have if only one of them is a success? 11. And then we have 12 choose 2 for 2 successes, which means I'll have how many failures? 10. Notice my exponents always add to give me n. 0 plus 12, 1 plus 11, and so on. So, for those that weren't here yesterday, this notation, so like 12 choose 2, just kind of off to the side here, that's a combination where we have 12 and we're picking 2. I know this one's a bit long, but type it in and let me know what you get.
How do you do the NCR again?
On the A4s, you have to type in choose virtual. You have to type in like the 12, for instance, and then you'll go to math.
Oh, it's math.
Then probability, and then you should see it.
Wait, how do you do on the
Inspire, you'll have to hit, you won't type anything in, menu, probability, and then combination. Menu, probability, and then combination. And then on the Inspire, you would type in, like for using this example, it would give you that, and you would do a 12, 2.
How do you get 0 up there on the exponent?
How do you get an exponent of 0?
Like how do you get the exponent that is the square?
There should be a button, I call it a caret, that looks like that.
like above the division sign?
Yeah, above your division sign.
Oh yeah, right there. I was looking at the second part. All right, thank you.
And you just put your exponent in there. If someone's wondering if they typed it in right, they don't know if their answer's right, you can ask me and I'll say yes or no. 3-9, yeah. At this point, 0. Yes. But yes, well. You had which one?
The one that we just said. 0028.
Yep, that's right.
We ran 4 days.
You can. Are y'all needing help?
I did it, but I did not get it.
Okay, let's see what I tried. Oh, there's a mistake that you wrote there.
Gotcha. Appreciate it. Lisa?
Second thing, don't choose to.
Yeah.
You take those supplements?
Oh, no.
No. I'm just curious.
The only thing that takes just creatine, but I don't know.
That's the probability of success.
What's that? 0.0028. There's our answer. Questions on this one? Okay, let's look at the solicitation example. Just here.
What is this for again? Binomial?
Binomial, yes. So it's where we have an experiment that can have we have a fixed number of trials, and then it can be either a success or a failure. And we're wanting to figure out the probability of having so many successes. Mm-hmm. Y'all remember yesterday how my deal kept jumping? Like I would write something and then that line? I think I figured out what it was. So I had this on and my Bluetooth. They're both Bluetooth. And this remote, this clicker on at the same time. And it was doing it. So I'm wondering if the Bluetooth wasn't interfering with each other. Because I turned this on today and the board started doing it. I turned it off and the board quit. What? Sounds like the Bluetooth was interfering. Weird. Anyways, totally off topic. Okay, so there's just the solution that we got. Okay, solicitation example. On the average, 1 out of 19 people respond favorably to a certain telephone solicitation. If 25 people are called, what's the probability that exactly 2 respond favorably? Okay, so first we got to figure out our N. How many people are we testing here? 25. What's the probability of success? 1 out of 19. What's the probability of failure?
18 out of 19.
18 out of 19. Okay, so they ask us the probability that exactly 2 will respond favorably. Probability of x equals 2. That's right. We're going to have 25, and we want 2 to be favorable. What will I raise my 1 over 19 to? 2. What about my 18 over 19? 23. So if you got an answer, what did you get? Yep. What you got, Raymond? Perfect. Two, 3, 9, 6. Questions on this one? Okay. Next one. What's the probability that at least 2 respond favorably? Oh. That's the probability that x is greater than or equal to 2. Now, do y'all want to sit there and do 2 plus 3 plus 4 plus 5 all the way to 25? No. What could we do if we don't go that route? No. 1 minus the probability that x is less than 2. Take the opposite. Take the complement. So if x is less than 2, what possible values could I have? 0 and 1. I think I'd rather calculate 2 values rather than 23 values. So I'm going to do 1 minus the probability that x is 0 minus the probability that x is 1. So if I set this up, 1 minus, and we're going to have to do 25 to 0. Remember, our probability of success was 1 over 19 to 0 times 18 over 19. How many failures did we have? 25. There's the first one, minus, and we're going to have 1 success. So 1 over 19 to the first power times 18 over 19 to the 24th. What are y'all getting? Yep, that's right.
On what?
3817.
0.3817. A good rule of thumb, if you didn't get that, but you're like, I think I entered it right. Check and make sure wherever I have parentheses that you have parentheses also. That could help. Questions on this one? Okay, next one.
We're not supposed to check that one by one. Just like, oh no, wait, never mind. We already.
Yep. We did that at the very beginning. Right there.
You get a fraction there. You get a fraction.
In the 84, you just do division. You just like the 1/19, you would just type in 1 divided by 19.
Or you could, it's math over, and then press alpha, and then the x minus 1 thing. That's a D, and it'll get you a fraction.
Okay, so let's look at the mean and standard deviation of a binomial distribution. So I have this on, I guess I should say not on yesterday, on Monday or yesterday. I had to say, okay, let's just try and write down the formulas real quick so you have them. Let's actually go over them. So for the binomial distribution, the mean is n times p. N, remember, is the number of trials. P is our probability of success. So we just do n times p to get the mean. For the standard deviation, it's going to be the square root of n times p times 1 minus p. Now, I'm just going to say this right now. I don't say 1 minus p right here. And what's that?
You call it Q.
I call it q. That's right. So q is equal to 1 minus p. I'm just warning you now, that's how I work the examples period, that's how I'm going to work on this period. I don't say 1 minus p, I say q. So this is really just equal to the square root of MPQ. And dual credit on the test, you'll have to do variance. Well, if standard deviation is the square root of MPQ, what do you think variance is? It's MPQ. Questions on the formulas? Okay. So let's look at this quiz example. I promise I won't be as mean as this professor is. So a professor routinely gives quizzes containing 50 multiple choice questions with 4 possible answer choices, only one of which is correct. Sometimes he just hands the students an answer sheet, so think of it like he's just passing a Scantron out, and tells them to guess the correct answers. No test, just a blank Scantron. Guess the answers. So let X be our random variable, being the number of correct answers on the exam. Find the mean and deviation for X. So clearly here we have a binomial where n is equal to 50. There's 50 questions. And since we have 4 answer choices and only one answer choice is the right one, the chance of getting it right would be 1/4. So to find the mean and standard deviation, well, let's do the mean. Mean is equal to n times p. So 50 times 1/4 is what? 12.5. Okay, they also asked for the standard deviation. So that's the square root of NPQ. So I know N is 50, P is 1/4. What's Q? Not P, which is 3/4. What would that give you to, let's do 3 decimal places. What's that?
3.0.
I think you just took the square root of NP. Don't forget we've got to multiply by 3/4. Oh, sorry. It might help if I look at the right example. I'm sitting here looking at the next example, like, no, it's 1 point something. Might help if I look at the right example. Sorry, guys. 3.062, yes. Once I looked at the right example and we established that was correct, any questions? Okay. So let's go back to our newborn example. How many girls do we expect in the next 5 births at a particular hospital? They're asking us about expected value, which is the same as what? Mean.
NB.
Yep, it's gonna be NP. What's our N in this case? 5. And what was our P from yesterday? 0.5. 5 times 0.5 is 2.5. So we can expect 2.5 girls. I want to know where the 0.5 came from. How can I expect 2.5 girls to be born? Okay, then it asks for what's the standard deviation. Oh. It's going to be the square root of NP cubed. The square root of 5 times 0.5. What's cube going to be then? 0.5. That's equal to what? This is the example I was looking at earlier.
1.25.
1.118.
1.118.
Oh, wait, square root.
And our units, again, are girls. Questions on that? Okay, so this isn't in your notes, so just kind of follow along here. So remember that in binomial distributions, trials need to be independent. So, however, when we sample, we typically sample without replacement, which means that they're not independent. I mean, if we think of our births example, the mother can't go in there, have a girl, and then say, nope, put it back. We don't want to count her. She can't exactly do that. So, they would not be independent. In this case, the number of successes observed wouldn't be binomial, but rather something called the hypergeometric distribution. You won't be expected to know that distribution. Just know that the calculations for probabilities in a hypergeometric distribution are even more tedious than the binomial formula. So when the sample size n is small, and capital N is large, the probabilities are actually pretty close to each other. That's why we're able to use the binomial. So if we sample without replacement, and N is at most 5% of our whole population, then the binomial gives a good approximation. Okay, so keeping up with the newborns example, let's entertain a thought right quick. Let's say that we're not interested in the number of females born out of the next 5, but we want to know which birth would result in the first female being born. Which birth would be the first female born? How is this question different from a binomial? What's different on this one?
How many trials before?
How many trials before the first success, right? So that's actually called the geometric distribution. So for dual credit, we just ended the test 2 material. If you want to maybe put a note, write something in your notes, end of test 2, or something like that, you can. Okay, so for AP, everything is game for the Chapter 7 test. Okay, geometric distributions. This topic kind of fits into a dual credit, like a gray area, in the sense that we're going over it, but y'all won't be tested over it. So what we just stopped with was the end of the test 2 material, but we're not quite to the start of test 3 material yet. Kind of caught in between. Okay, so for the geometric distribution, the first few properties should sound familiar. We need 2 mutually exclusive outcomes that can result in either a success or a failure. Each trial must be independent of the others. The probability of success is the same for all trials. So far, we're sounding like a binomial distribution. Here's where the curveball comes in. For a geometric random variable, we're interested in the number of trials until the first success is observed, including that success. So how far are we going to go before we get to the first success? So what are our possible values of x? What could x possibly be? Let's say I'm flipping a coin and I want to see how long it takes before I get heads. It could be 1 flip, it could be 2 flips, it could be 3 flips, 4, 5. Is there any sign of stopping? No. So how far will it go? To infinity and beyond. This goes to infinity. I mean, theoretically, you can flip a coin 100 times before you even get the first heads. It's not likely, but it can happen. Okay, so let's look at formula. Let P be the probability that we get a success. Then our formula for the geometric is P of x equals 1 minus P to the x minus 1 back times P, where x is equal to 1, 2, 3, and so on. Okay, let's put this into practice. So suppose that 40% of the students who drive to campus at your school or university carry jumper cables. So for those of y'all that drive, how many of y'all carry jumper cables? 1, 2, 3. Okay, those of y'all that don't, now you know who to go to when you break down. If your car has a dead battery and you don't have cables, then you're going to stop students as they're headed to the parking lot and ask them whether they have a pair of jumper cables or not. So let's say X is the number of students that you stop before finding one with a pair of jumper cables. Because, I mean, let's be honest. Once you find the person, are you going to stand there and keep asking? Yeah. If they're willing to help you, you're going to get jumped off and then you're going to leave. So is this a geometric distribution? Yes, it is. Okay, so let X be the number of students stopped before finding a pair. That means the probability of success would be 0.4. So what's the probability that the third student stopped will be the first one to have jumper cables? That is, we're looking for the probability that X equals 3. That's going to be 1 minus 0.4. Now, how many did you have to ask that did not have any? 2. So 1 minus 0.4 squared times the one that finally did and rescued you. So what would this probability be? Get it, Stephen?
Is it 1/4?
It is. Zero 0.144. Okay, now we want to know what's the probability that at most 3 students have to be stopped before finding one with jumper cables. The probability that X is less than or equal to 3. Or how many could we have to ask, possibly? 1, 2, or 3. So we need to do the probability that X equals 1 plus the probability that X equals 2 plus the probability that X equals 3. Okay, so what's the probability that the first one is a success? Because I want to kind of illustrate something here. What's the probability that we go to the first person and they're successful? 4. Now, these are independent people. So the probability that the second person is successful means the first one was a failure. That's going to be 0.6. And we have a success. So times 0.4. Then the second one, we have 2 failures and a success. So essentially, each time we're multiplying by another failure. That's all we're doing here. So what do I get when you multiply these?
What's that,
0.784. Good.
Is this in the homework due Sunday as well?
No credit's not responsible for anything dealing with geometric.
Oh, that's just not-
the formula?
What's that?
Can you go back to the-
Yeah, sure. One there also. Yeah. There we go. Mhm. Okay, so that's the solution to our problem, of those problems that we solved. 0.144 and then 0.784. The next one, over a very long period of time, it's been noted that on Fridays, 25% of customers at a drive-in window at the bank make deposits. What's the probability that it takes 4 customers before the first one makes a deposit? So basically, the 4th customer is your deposit maker. Okay, I just shrunk it so I have room to work here. So, what's our probability of success on this one? What's our P? 0.25. And it's going to take, we want to know the probability that it takes 4 customers. The probability that X equals 4. Well, if the 4th one is our success, how many failures did we have? 3. What's the probability of us being a failure? 0.75. So we're going to have 0.75 to the 3rd power. Times our success of 0.25. So what would that be? .1055. Good. Okay, questions on the geometric distribution? Okay, so now this is where your credit your test 3 material starts. We're about to start 7.6. And started test 3 material. And this is also where the homework I just gave you comes into play. Okay, so 7.6 we're going to be introduced to the normal distribution. I mean, we were kind of introduced to it, calculating z-scores, but now we're really going to be introduced to it. Like, hello, here I am. You'll use me for the rest of the semester. So the normal distribution is probably the most infamous continuous probability distribution. It's symmetrical and bell-shaped, and is defined by mu and sigma, the mean and standard deviation. Regardless of what our mean and standard deviation are, the area under the curve will always equal 1. And the probability of observing a value in a particular interval is calculated by finding the area under the curve. It's just like we learned when looking at continuous distributions. You gotta find the area. Now, I don't know about y'all, but even in college, we did this formula for the normal distribution. I'm not gonna show it to y'all. I promise you, it looks horrendous.
What?
For the normal distribution. Like the actual mathematical formula that you would use to graph it. It's horrendous. It's like e to the something, something, something. I don't even know. I don't even have it memorized. That's why we have the tables. We're going to use these the tables. So as sigma increases, the curve flattens and spreads out. And someone charging, whoever was charging their phone back there, it just went.
And I was calling my phone.
Yeah. So as sigma increases, our curve will flatten and spread out. So if you look up on the screen, this isn't in your notes, but if you look up on the screen, the curve drawn in this bottom right corner right here, that's just our standard normal. We'll talk about the standard normal here in a second. But as sigma increases, look what happens to the curve. So it goes from that to that. As sigma increases, as our standard deviation increases, think of it like someone just stepped on the curve. It's an ant bed that you just stepped on. As sigma decreases, as the standard deviation decreases, the curve gets taller and thinner. There's our standard normal. Watch what happens as sigma decreases. Okay. So normal, sigma decreased. Okay, so the notes are slightly out of order here. So let's flip over to page 18 for a second. Okay, so we have this little small slide activity here. The mean, remember, is on a symmetric distribution, the mean and the mode are the same. So our mean goes through the highest point of the graph. That is a horrible one. So if we draw like a line to the tallest point, and I can't draw a straight line, but anyways. So do these curves have the same mean? Yes. What is that mean? Assume the tick marks are just ones. Yes. Okay. Which normal curve has a standard deviation of 3? Remember, your normal one is a 1. Which one would be a 3? The flatter one or the taller one? It would be the shorter one, B. And the way we know that is because B is a lot flatter. Our options here on this example were 3 or 1. B's the flatter of the two, so that means it's going to have the bigger standard deviation. What was that?
Standard deviation on this of 3. What would that be?
Or would that be B? See how flat the curve is? That means it's more spread out. You have more values going further from the mean. The other curve has a standard deviation of 1. So I mean, it asked you, but we already said B for 3. That means A has a standard deviation of 1. See how close A is together compared to B? That's why B is 3, A is 1. Okay, let's flip back to page 17 now.
So,
Yes.
right? Right.
Okay, so for the standard normal distribution, it's a normal distribution with a mean of 0 and a standard deviation of 1. So when I just say a normal distribution, that can mean any mean, any standard deviation. The standard normal only talks about 1. It's the distribution that has a mean of 0, standard deviation of 1. And for the standard normal, it's customary to use the letter Z to represent a variable whose distribution is described by the standard normal curve. So back in chapter 4, when we were finding z-scores, this was gearing us up for this. So our z-curve is just the standard normal curve. Okay, now we can flip back to page 18. This is one of those tables that I passed out to Joel Credit, and then the ones I mentioned in your formula chart for AP. This is where those tables will come into play. So for any number z star, from negative 3.89 to positive 3.89, and rounded to 2 decimal places, you can look in your book in the appendix on table 2, or it won't go quite as far, but you can look on those charts that I gave you. I think it goes to negative 3.49 to positive 3.49. It doesn't go quite as far. On the AP formula chart, I'm not sure if it goes all the way to negative 3.89 or not. But most charts at least go to 3. Negative 3 to positive 3. So when we use the letter Z and we use these charts, it's the area to the left of whatever value you have here. Show me a diagram. Okay, so let's say down here I have a graph, and this is my Z that I'm interested in. The probabilities in the table will always give you what's to the left of it. It'll never give you the right. You have to calculate the right, and we're going to talk about how to do that, but just know it's always going to be to the left. So to use the table, you find the correct row and column, and we're going to do some examples. And the number in the intersection of that row and column is our probability. And until you really see this in action, it just sounds like a bunch of Greek. So if you look in the textbook, I'm not sure if that page number is accurate or not. The PowerPoints have kind of been inaccurate on page numbers. But I know it's in Appendix 2. I do know that part. They also have the tables in there. Let's just jump into look at an example. You can read the steps, but like I said, you can read the steps all day. Until you actually do it, it's going to look like and sound like Greek. So the way we read this, the way we use our probabilities here in the chart, you take the first 2 numbers here. So this number could be a 0, it could be a negative 1, 2, 3, whatever, just the first 2. That's what you're going to look at down the first column. This is an abbreviated table, it's not the full table. But our first 2 numbers are negative 1.6. So down my left column, I'm going to look for negative 1.6. That's the row I want to start with. Then I look along the top row for my last number right here, a 2. So I go to 0.02, 200ths. I'm going to look in that column. Now I have my row and my column. I'm just going to go until my fingers meet. You can't do this draw at the same time, but boom. They would meet right there. That means my value is 0.0526. 0.0526. Okay, let's look at the next one. So now let's say we're interested in the probability that z is less than 2.31. So here's our table. What number do I look for over here on the left? 2.3, the first two digits. So I'm going to go down until I find 2.3. What number do I look for along the top? The last one, the 1. So here it is. I'm going to go along until I meet. And that's going to be my value. So this probability is equal to 0.9896. Okay, let's flip over. Before we do that, let me ask, is anyone confused? Because I just went through those kind of quick. Is it making sense how to read the table? The homework I gave y'all today, dual credit, probably about 60% of that homework is just can you read the table. You may have to do a little bit of manipulation like we're going to see today and tomorrow, but the bulk of it's can you read the table and get values. Okay, so now we're going to, notes-wise, make our table even bigger. You can't just use a small table the whole time because that's not what you have. So now they want the probability that z is less than 0.46. So what number do I need to look for then over here on the left side? 0.4. Look for that number. Circle it. Now I'm circling these. I don't really recommend. On your notes, you can circle it because you have this chart printed in your notes. But on that one that I gave y'all, I wouldn't circle it because then you're going to have all these things circled and you're like, what the heck am I looking at anymore? Okay, so there's 0.4. What column do I look at? 0.06. I'm going to follow those until I meet. Now when I meet, let me know what value you get when you meet. So what value, what probability did we get when they intersect? That's right, 0.6772. Now we're growing our table. I'm giving you an even bigger piece of the table. Okay, so they want us to find the probability that z is less than negative 2.74. What do I look for in that column? That very left column. What's my first number I need to look for? Negative 2.7. There it is. And then what column do I look in? 0.04. So then what value will I meet at? 0.0031. Do we feel okay dealing with these tables? Okay, so let's suppose now that we're interested in finding the probability that z is greater than 2.31. That's great and all, but what values do the table give us? Does the table give us? Less than. How can I use the table? So I'm interested in greater than, but the table only gives me less than. So I'm going to do 1 minus the probability that z is less than 2.31. And we actually found this value in example 2. So just to save us some time from having to look at our table again, what did we say that value was in example 2? 9896. So I'm going to have to do 1 minus 9896, which is equal to what? .0104. Okay, so there's a blank right by that example. It says the table areas give the area to the left of z, which we already said. But to find the area to the right, we subtract the value in the table from 1. So in that blank by that example, we put a 1. So right quick, I want y'all to try to do parts A and B of example 6. I'll give y'all like 30 seconds. So what did y'all get for part A? .9664. And what do we have to do to get part B? Okay, so subtract it from 1 on part B, and you get .0336. And so if you got that done, I'm going to leave the screen up in case someone's trying to get it written down. If you leave that done, if you have that done, flip over and try to do C and D right quick. Going short and then or something. What did we notice for C? What was C equal to? 0.0336. I feel like I've seen that number before. Okay. What about D? What did y'all get? $9,664. Again, I feel like I've seen that one. So the reason these work out like they do is something called the symmetry property. So notice that from the preceding examples, the probability that Z is greater than a certain value is the same as the probability that Z is less than the negative of that value. If we have two possibilities here, probability that Z is greater than negative 2.18 and the probability that Z is less than positive 2.18, then they're the same thing, same exact thing. And again, we didn't get to where I wanted, but that's okay. We stayed consistent. We stayed about a page behind since Friday, so. I do want to go over one more property, though, just to keep us on the same track as third period. So I will say this class was slightly behind third period. So the probability that a continuous random variable x lies between a lower limit a and an upper limit b is the area to the left of b. So this whole area minus the area to the left of A. I'm only interested in the part between A and B. But if I just did B, that gives me something I don't want. So we need to take it out. Now, I mean take it out on the date either. We subtract it out, subtract A out, and that gives us our desired probability. So that's what you would put where you have like that equation of two graphs. That's what y'all would write near that graph equation. That's where we're going to stop. I'll leave that up there so you can get that written down. We'll start with example 7 tomorrow. If you move the calculator or something, if you don't mind putting it back on the desk that you moved it from, I would appreciate it. Thank you.